Welcome back. This time we'll do a paper 2 higher walkthrough of the Specimen series. If you haven't watched already, I'd recommend you also watch my paper 1 version, however it doesn't matter what order you do it in. And one very useful thing about exam questions is that it tests your ability to understand not only the content but how it's assessed. The best way to be prepared for the exam is to do the exam questions itself that you'll face. And that's the reason why everyone mentions about exam technique. And it's mind-blowing just how much content they can fit into 2 papers, even if they don't cover all of it. They cover a good chunk out of it, and you'll see throughout this whole Specimen series, you need to use quite a bit of knowledge here from the whole course. So I hope you find this walkthrough helpful. Now there'll be a link below in the description to also do this paper with me. I recommend you do it before I start the video or before I walk through it, and you do it in silence exam conditions. You'll then be able to watch how I go through the questions and note down any weaknesses. And if you need the formula sheet, well, here are the formulas that you need to know. Number 1. Tracy wants to find out what improvements to the youth club are wanted by the members of the club. She plans to give each member of the club a questionnaire. Here is part of the questionnaire. We have 5 questions and here they are. Part A asks us to explain why question 2 will not give reliable results. Before I resume this, I just want to point out that this is such a nice question for 4 marks in total, because you can, if you know the content, do this so fast, and it makes those harder questions later on, gives you a bit more time, and just reduces the stress a bit. Back to the question. Why question 2 will not give reliable results? Question 2 asks us to input our age. We have 10 to 12 years, 12 to 14 years, and 14 to 16 years. Take a minute and pause. Think about what is wrong with this. And there are 2 blaringly obvious issues with this. The first one, if you're a 12-year-old, do you select this box or do you select this box? Because by this question it indicates I need to select both of them. And the other one, although less obvious, though if you did spot it you could also put it, what if you're 9 years old or 8 years old or perhaps you're 17, even though youth clubs go up to typically 18. So it's missing out ages, so there's a lot of issues with this, and I'll go with that, but there's overlapping categories. Part B. Explain why question 3 is not a good question. Do you agree that the condition of the club needs improving? Now, it's not really obvious from the specific example. Try and think of it like this. If I approach you and ask this, Mars is a good chocolate bar, right? Well, you're going to feel inclined to say yes. You don't want to offend me, but let's be honest, if I asked you what your favourite chocolate bar is, it might or might not be Mars, and there's a high chance that it would not be Mars because there's so many other options available. So this is called a biased or leading question, because it's more of a psychological point in that you're pressured to say yes or no depending on how the question is worded. For example, my one was yes. If you go to someone and say, do you like the specific chocolate bar? Well, they might say yes in the moment just to not offend you, and that's a good way to think about it. As I previously mentioned, this is called a leading question. Part C. Explain why there might be a problem with the answers given to question 4. So let's look at question 4. How much time do you spend in the youth club? Well, I can put this. I can put 2, I can put 91, I can put, I don't know, I could put anything. Now, you can see what the problem is here. I could also put this. I could put 20. Now, it might be all nice and fine if a human is going through this, but, well, let's say there's a massive club and you're going to put it through a computer software to automate this. Well, how is it going to process, I don't know, and 20 when it's trying to look at integer inputs? It doesn't have to be integer inputs, it could be the other way around, it could be that they only want letter inputs. So it's going to make the data hard to handle. And we actually call this an open-ended question, rather than these tick boxes, which are called closed questions. This is an example of an open question, meaning you can give multiple different answers, and there's basically endless possibilities. Part D. Explain why the answers given to question 5 may not be valid. Do you know someone who has caused damage in the youth club? Well, if someone you know, perhaps your friend, or perhaps it's someone you don't want to snitch on, well, you're probably going to say no. And another thing is that this isn't anonymized. It's quite clear that Tracy here is giving it to each member, and I'm going to assume physically. There's nothing about anonymity here, so we can't really assume that. And this is a sensitive question. And that's what the mark scheme wants you to understand, is that this is a sensitive question, so you're not going to really tell the truth in this specific, or you might not even answer it at all. There you go, awful spelling of questionnaire, but that's that. 2. Matthew recorded the scores in a memory test taken by some teenagers and their parents. The teenagers took the same test as their parents. The box plot shows information about the recorded test scores for the teenagers. The table gives information about the recorded test scores for the parents. On the grid above, draw a box plot for the recorded tests for the scores of the parents. So I don't even have to tell you what a box plot looks like, because they've kindly given us one here. As you can see, we've got the box at this part here, and then we've got these lines coming out of it, and perpendicular to that, we call these things here whiskers. So what does all of this represent? Well, they've actually kindly given us this table here, and it illustrates perfectly what a box plot contains. A box plot contains the least, the lower quartile, the median, the upper quartile, and the greatest. And here the context is around scores, and that's why they've labelled it scores. So here we've got our least, and I'll just label that L. This is our greatest value, I'll label that G. And then we have these 3 parallel lines, which are vertical. This one here, and this one here. Everything I shade from this region to this region, or in this side of the rectangle, is from what we call the lower quartile all the way to the median. The median, as you'll probably know, is the middle value. However, you might have not heard of lower quartile and the upper quartile. The upper quartile, and I'll abbreviate this one to UQ, upper quartile represents 3/4 of the data through, whereas the lower quartile represents 25% of the data through. And you'll obviously know that the median is the middle of the data set, it represents 50%. So the lower quartile is 25%, the median is 50%, and the upper quartile is 75%. You might want to take these into account. This is the 25% value of the data, this will be the 50% way of the data, and this is 75% of the way through the data. So we just have to plot this. So it's quite simple. You need a ruler. I recommend you do it in pencil, so you'll be able to trace over if you make any mistakes, because you don't get any second graphs in the exam, and if you mess it up, well, that's your mark gone. So what I'm going to do is I'm going to plot first the least scores. I'm going to make my way chronologically. You could, if you want to go through any of the other ones, for example the median or even a greatest score, it doesn't really matter as long as you just do it and just try to be as accurate as you can. Now I'll do the lower quartile. And I'll move to the median and the upper quartile. And then lastly, the greatest score is 39. And now I just need to connect these. I'll connect the top to make the box of the box plot. And then connect the whiskers to the actual box itself. And that is pretty much the diagram. Now, if you get all of those plotted, that's a free 2 marks. And at the end of the day, if you practice these, then it will be second nature. Part B tells us to compare the distributions. We need to give 3 comparisons and interpret one of them, and that's probably going to be context. So let's label the key thing. We're going to compare their distributions. Now that should instantly throw loads of words at you, and we'll go through those in a minute. And we have 3 comparisons, and of those we need to interpret one of those comparisons. Now, interpreting, instantly you think context. The 3 comparisons will be related to the distributions, and when you're thinking about that, you always go to the defaults. The defaults will always be median, and I'd always choose median. And then you can have one of IQR or the range. However, I always recommend going with the IQR. It's one of the safer bets, and it's just more statistically, it's a better measurement. So the mark scheme also tends to favor that. But you can use the range if you really want to. And then the other one, because distributions came to mind, was skew. So then let's look and actually go to the box plots. Now we can see the median at the teenagers part, if you read it off, is approximately, or it is at 31, which is here. And we can see that the median we've been given was 29. So we can say the median of the teenagers was greater than the median for the parents. And that's your first mark. The next one we're going to look at, now we've ticked off median, is IQR. And I'm not going to look at the range, I'm going to choose to do skew. Now we need to remember to interpret one of these, and I'm going to choose to do the IQR. You could well easily do the median. So for the IQR is another piece of information that you might not know, so I'll give it here. And the IQR is taken by getting the upper quartile and subtracting the lower quartile. So it basically finds the middle 50% of the data, everything within the box plot here. So we can see that the IQR for the teenagers, if we look at it, well, we can get this point to be 35, and this point here for the lower quartile, should probably say in this, is 24. So the lower quartile is 24 and the upper quartile is 35. What's the IQR for the teenagers? Well, we can just do 35, subtract 24, and we get 11. For the parents, well, we just got our ones here. We can use our upper quartile of 35, and we can also use our lower quartile of 21. 14. So the IQR for parents is greater than the IQR for the teenagers by our calculations. We're going to also write that. Now this is one of the safer bets to put your comparison or your interpretation in, so I'll put it here. And what can we gather from a higher IQR? If the IQR shows the middle 50% in your data, and IQR value for the parents is larger than the teenagers, that indicates that there is a larger difference in the middle 50% for the parents than the middle 50% of the data for the teens. So what we can say is that the teens tend to have more consistent memory scores on their tests. Okay, so we've done that. Now we're going to look at skew. So when you're looking at skew in a box plot, you need to identify if it's either positive, negative, or symmetric. Or let's just put none. They're both basically equivalent. So if we have a box like this, we need to identify what this looks like. And they're both not symmetrical because they have the split, which isn't exactly in half. And you can see that the left side tends to be more than the right side. If you can see it, it's just about, and you can count them by squares if you want, and you can see that the left side is indeed bigger than the right side. So I'd illustrate it something like this. Now, intuitively, you'd actually think that, wow, this is more towards the positive axis, so this will be some sort of positive skew. Well, again, I'm just going to flip it on its head, and this is going to be negative skew. It appears to be positive because the line that's dividing it is more in the positive region, which would associate with the right side. However, it's actually negative skew. And you can see both of these have negative skew. And that's just going to be my last point. So you get 1 mark from the top one, and then a mark from your second comparison, the context mark, which was your interpretation, and then your last distribution mark for the comparisons. Part C. The information for the teenagers is based on data collected from 56 teenagers. Estimate the number of these teenagers whose recorded test score was greater than 24. Okay, it wants to give us an estimate for the number which was greater than 24. So we're looking at the teenagers one here, the teenagers box plot. Greater than 24. Well, if that rings a bell, this was actually the lower quartile, because we earlier recognized that here. So if we're looking at an estimate for the number greater than 24, that's going to be everything to the right of that point. And we also saw that the lower quartile is 25% of the way through the data. If you imagine that, we have 25% of the data here, and then the rest of the data here. And the data needs to add up to 100%. So how much data is this here? Well, we can see that that is 75%. So we know that if we're looking for the estimate for the number of teenagers who was greater than 24 or greater than the lower quartile, we know that 75% of teenagers scored greater than 24. And now we can use that information and find that 56 out of the 56 teenagers, we had 3/4 or 0.75 of these scored greater than 24. And I'll just type this into the calculator. 42. Julie was investigating the relationship between the marks gained by students in their GCSE maths exam and then the marks gained by the same students in an A-level maths exam. Suggest a hypothesis Julie could use. Well, the same students take both of the exams, so I'm going to guess that in order to progress to A-level they must have done well. Therefore, students who score highly in GCSE maths should also score highly in A-level maths. Julie drew a scatter diagram using the marks gained in GCSE maths and the marks gained in A-level maths by each of the 12 students. For this scatter diagram, explain why GCSE maths is the explanatory variable. Now, there's 2 types of variables we have, is the response and the explanatory. Now, if we switch to science for a minute, you might know the response variable as the dependent variable. And you guessed it, explanatory is the independent variable. And the reason for this is that, well, you're going to take A-level maths after GCSE maths. So if you're taking GCSE maths before and you get your result for that, you can kind of see how you're going to do in the A-level, as it's going to respond to basically how clever you were in GCSE. Not that that is really truly correlated, because you can't change in that 2-year period. But the idea is that you sit GCSEs first, and they're plotted on the x-axis, and the x-axis is where you put your independent variable every time. Part C. Explain, given a statistical reason, whether or not the scatter diagram supports your hypothesis in Part A. Well, our hypothesis in Part A was that if you do well in GCSE maths, you will do well in A-level maths. And what does a statistical reason mean? A statistical reason is any sort of measurement we can use on the graph. Now, there's a few I can think of: skew, gradient, correlation, and obviously the gradient is the correlation. And we can see that this one has a general positive correlation, is going upwards, like so. So it's a positive correlation. I need to just grab this out real quick. And because of that, well, we can see that our hypothesis is supported. Because as you can see, those with a lower mark in GCSE tended to get a lower mark in A-level maths, and the positive gradient or the positive correlation has shown that as you get a higher GCSE mark, you're more likely to get a better A-level mark. Using statistical software, Julia obtained the following information of her 12 students. The mean mark for the GCSE and A-levels are shown here, and the gradient of the line of best fit. What these give us is the double mean point, which is shown with x bar, y bar. As is, it's just the average of all the x values and the average of all the y values. We can clearly see that the x values here are our GCSE ones, and our y ones are your A-level maths. So we can kind of write this in the x bar, y bar format with the GCSE and A-level respectively. So that does give us 578 as our x value and 78 as our y value. And the idea of a line of best fit is that it goes through the double mean point and it also has the gradient. And the gradient is 0.7. Then the mark scheme does give you a leeway. It makes sure you need to make sure your gradient's between 0.6 and 0.8. But it's just good practice to nail it down first try and get 0.7 and not leave it a chance. So to do this, you're going to pick 2 points and you need to try and achieve a gradient of 0.7. Now we know that the gradient is equal to the change in y over the change in x. So it's going to make sense to try and plot our double mean point, 578 for the x and 78 for the y. I'll do that now. So now that I've done that here, we've got to plot a line through this part here with a gradient of 0.7. Now we've got to try and be as accurate as we can be, close to 0.7, and we can write 0.7 as any fraction equivalent to 7 over 10. This can be 14 over 20, it can be 70 over 100, it could be 35 over 50. For all we know, we could use any sort of scale. So I've decided that I'm going to choose 14 and 20. Now 14 over 20 is your y over x, so our x is actually 20 and our y is 14. This is some unorthodox method, but you can see that if you subtract the coordinates from each other, and please don't use this as an official method, and to be fair, this isn't a method mark, this is just how you're going to work it out. You can see that we get 558 and 64. And now when we join this up, if we actually find this point, 558, 64, now if we join these two together, and this is what we get. So we go along from 558 to 578, which is along 20, and we're going up from 64, sorry, and we're going all the way up to 78. And you can see the gradient is 14 over 20, or the equivalent of 0.7. So you've met the conditions that it goes through the double mean point, which is here, and then you've got a gradient of 0.7. Now that was a tough one, and they did give you a range of 0.6 to 0.8. That said, use some sort of method to make sure you're not very off, and don't do it by eye, because again, that could quite easily look as a gradient of just 1 rather than 0.7. Part E asks us to interpret the gradient of the line of best fit. Now the gradient of the line of best fit is 0.7. Now what does that exactly mean? If we go to a molecular level, for each mark we go and increase by 1, you can see a slight increase, but not exactly 1 for the A-level maths exam. If we extrapolate this a bit more, we can see that if we go across 10 marks, well, we get something roughly approximate to 7. So for every 10 we go up 7, and as you can see here, this one, as we went 20 along, we went 14 up. So you can see that for each additional GCSE mark we get 0.7 additional A-level marks. Julie wants to use the line of best fit to predict the A-level maths mark for a 13th student. For GCSE maths, this student gained a mark of 540. Explain whether or not it would be appropriate to use a line of best fit to make a prediction. Well, let's see. The 13th student got a mark of 540. 540 lies on this X line. Now, as you can see, that is outside the data range, and the data range, as we can see, was everything from this X point all the way to this X point, because the most outer values are this one and this one in terms of X. So if we're estimating for a value that's outside this data range, well, the first thing is it's not going to be reliable, and hence it's not going to be appropriate. And the reason we can give is that it's extrapolating or it's outside the data range.